Okay, so welcome back from the coffee break to the second part of the afternoon session of our Topological Material Conference. And our next speaker, it's my great pleasure to introduce the next speaker. It's Maia Vergniory. She's based in Spain at the physics, at the Donostia International Physics Center. And Maia is an expert in topological materials, in particular in the theory. First principle is modeling, but also group theory, and always with an eye also to transfer this knowledge to real materials. And she has very impressive papers. For example, one with a title which I found very impressive: "All topological bands of all stoichiometric materials." I think this is really impressive. And Maia, we are very much looking forward to your talk, which will deal with topological semimetals. And yeah, from theoretical prediction to material realization, and the stage is yours. Please go ahead.
Okay, thank you very much for this very kind introduction and for inviting me to give this talk. I wish it was happening where it should have happened, but okay, better times will come. So yes, I'm going to talk about topological semimetals in this talk, and I want to show you how we can go from theoretical prediction using group theory and mathematics to actually experimental material realization. So the modus operandi is the following. We start classifying the topological phases using, as I said, group theory and topological invariants. We are in the weakly interacting regime, so we are allowed to do that. And then we try to realize these topological phases in materials, first predicting these properties using ab initio techniques like density functional theory, and then talking to experimentalists to realize them in materials. And finally, we collaborate with more phenomenological physicists and experimentalists to be able to detect these properties and prove that the prediction was correct. So with this, I'm going to present you the outline. First, I'm going to give an introduction to Weyl semimetals, and then I want to explain to you what is the concept of ideal bisemimetals and Nodal lines. Once I have introduced the topological phases that we are interested in, I'm gonna show you very efficient search engine, and I'm gonna focus on magnetic topological semimetals. And afterwards, I'm gonna also talk about a specific search for multifold nodal points in these topological semimetals, like the multifold magnetic nodal points. And then I'm going to end this talk with presenting some experimental realizations in collaboration with some experimental friends. So electron dispersion has a curvature because electrons have a mass. However, in 1929, Hermann Weyl predicted the existence of massless electrons, still with a charge, by canceling out the mass term in the Dirac equation. This was a fantastic prediction because the electrons dispersion was the same as the speed of light. And since we know that no one can travel faster than the speed of light, the solutions to this equation were in this shade area. 90 years later, particle physicists are still looking for these massless electrons. Neutrinos were candidates for some time, but now with some neutrino oscillations, it seems that neutrinos also have a mass. And the search continues. I mean, finding a massless electron would be a technological revolution since 80% of the consumption is wasted. And of course, a massless electron would cut down the resistance. A solution, however, was found in condensed matter physics. When we are inside a crystal, we can arrange the environment such it mimics if the electrons could have a linear dispersion. Meaning we can engineer our crystal in a way that our band structure can have a nodal point with a linear dispersion in the brilliant zone. Of course, now we are bounded by the by the brilliant zone, and the momentum and the dispersion will be linear, but we will not reach the speed of light. And also these are quasi-particle excitations. They do not exist outside the crystal. The moment we pick up an electron from a crystal, it will acquire a mass and the linear dispersion will be destroyed. But still, this is very interesting because of course, they are also massless electrons. So in order to look for application, apart from the fundamental discovery, what we would be interested in is finding a single pair of Weyl points close to the Fermi level and with an energy window free of other bands. Because we are in the brilliant zone, we always go from, because we are in the brilliant zone, Weyl points come in pairs that go from K to minus K, and they are related either by time traversal symmetry or inversion. So when we look for materials, this is what we would like to find: a single pair of Weyls that actually are close to the Fermi level and clean of irrelevant bands. If we want to look for this type of material, we need to break time reversal symmetry, otherwise they come in two pairs. So this is a summary of what has been discovered in the past year. Probably I need to update it, but it shows a little bit the search of material that has been done in the search of this ideal Weyl material. So in this column, we have the crystal. Here we have the pair of Weyl nodes, how far close are from the Fermi energy, and if they do have or not irrelevant bands. This would be our ideal material, and there is none candidate yet. And the closest material that was actually predicted theoretically was this alloy with a pair of Weyl nodes close to the Fermi level, but then it was surrounded by irrelevant bands. So the search of the ideal semimetal still continues. In 3D, bands can also cross in a plane, creating an open or closed line that we call a nodal line. These nodal lines are actually very interesting because they support weakly dispersion and with weakly dispersing surface state that actually can induce to correlated physics. Also, these gapless nodal lines are protected by symmetry, and in particular, they are protected by the reflection symmetry because the lines have opposite mirror eigenvalues. And as distinct from topological insulators, they do not show topological surface state in every surface, only the ones where the symmetry that protects the nodal line is preserved. Nodal lines are very interesting, but they are also very difficult to detect because the surface state that we find in the surface where the symmetry is preserved is a projection of all the K points along the line, and usually they get messy and mixed with the bulk bands. So it's quite challenging to actually identify another line in a material. Okay, so these are mainly the most interesting topological semimetals that we have nowadays in research. And now I'm gonna show you how can we look for them in a quite efficient way. So I'm going to introduce the magnetic topological quantum chemistry, which is a search engine. But before that, before introducing magnetism, I'm just going to do it without magnetism when time reversal symmetry is preserved. And for that, I need to talk about the atomic limit. So this is a concept that we use a lot in our field, and it seems the following. So we work in reciprocal space and we have block states, but with the block states, we can actually say nothing about the localization of the charge in real space. If we want to talk about the charge in real space, we need to consider the Maia state, which are the integral over the block states in the brilliant zone. And they are periodic, they form an orthogonal basis. And when we look at the center of the Maia state, what we have is the localization of the charge. Okay, so whenever this Maia center is located at the atomic site of our crystal, we call this situation atomic limit, and this describes actually a non-topological insulator. When the charge is located at the atomic site, we fulfill the atomic limit and we have a trivial state. All right, so the search engine is basically based on this concept. reformulate in a different way that actually was formulated before Vanderbilt and Soloyanov talk about the atomic limit, and it's the elementary band representation. So elementary band representation is a set of bands that are connected in reciprocal space, and they are defined by three ingredients: the orbital, the atomic site, and the space group, or the irreducible representation in real space, the Bykov position, and the lattice. I mean, in this particular case, we have the honeycomb lattice, we have the 2D Bykov position, the hexagonal space group, and the S or PC orbitals. And if we go to reciprocal space, these bands are going to be connected, and they are going to be described by the symmetries of the wave function of the high symmetry points whose characters have been tabulated. And the key concept here is that an elementary band representations represents actually nothing but the atomic limit. So whenever we have bands induced by these three ingredients and the charge is located in the atomic site, we have a trivial phase. Now, in order to use this concept to predict topological phases, we need to look at the compatibility relations. So the compatibility relations tell us when two high symmetry points are connected. So if I have K1 and K2, two high symmetry points, they are going to be connected by the line Ki. If we can find a set of parameters that actually fulfill both, can reproduce both high symmetry points, which means that this line has to be a subgroup of these 2 points. Okay, so with this idea and elementary band representations, we face 2 situations. One, our bands fulfill the atomic limits and they are connected. And in this case, if we are below the Fermi level, nothing happens. But if the filling of the electron is such that we have empty conduction bands, the compatibility relations will not be fulfilled before the Fermi level, and therefore we will find a protected metal. And when we have a protected metal, we have chances of having topological crossings. Depending on the dimension of the crossings and the crystal symmetry, of course, this will give us hints, but at least we have a starting point. Or our bands, somehow they, the little groups swap and we open a gap. The little groups can swap, for example, with a strong spinor recoupling. So the bands stop being connected, and then we will have a topological insulators because the atomic limit will not be fulfilled. Okay. By doing this, which is just looking at the symmetries of the wave function at the high symmetry points and the properties of the little group, we could identify many topological materials. And we have uploaded them in this website, which is public, and you have the information about the material, the brilliant zone, the lattice parameter, the electronic band structure, density of states, the gaps, the little groups, and the topological phases. All right. So natural extension would be to go from the non-magnetic formulation to the magnetic one. But actually this was, even though it was natural, it was not straightforward because we needed several tools that were not actually implemented anywhere, like the magnetic representations. There was this book, the Bradley-Ackronet, but it was incomplete. So a lot of work needed to be done just implementing the magnetic properties of magnetic groups. So this was done. Then there were no magnetic DFT codes in a sense that we can do magnetic calculations in the state-of-the-art DFT codes, but the magnetic symmetries are not saved. I mean, we only get information of the spatial symmetries. So interface needed to be implemented in this particular case with VASP to actually have access to the magnetic symmetries that the elements, the compounds carry. And this was done too. And there was no magnetic classification in the same way as in topological quantum chemistry, let's say something that can identify the phases fast. And this was done too. Okay, so the group theory tools and symmetry tools were done. And they are all updated in the Bilbao crystallographic server. And now we needed to deal with the first principle calculations. So there are many databases with non-magnetic materials that crystal structure has been identified by X-ray diffraction. but there are very few databases that have actually the magnetic structure. So for that, we consider the magnetic database of the crystallographic server. They only upload structures that have a magnetic structure realized by neutron scattering, so it's reliable. And we use the experimental magnetic structure as an input for our first principle calculations, because calculating the ground state with first principle might lead to a wrong ground state. And also considering all the possible magnetic configurations is nearly an impossible task. So we consider the magnetic structure of this database, and then we perform first principle calculations. Magnetic materials have a correlation. So in this way, in order to have like a phase diagram of all possible topological phases for different parameters of U that will take into account correlations, we calculate the band structure and the topological properties for the different values of U, in a sense that if you have a material and you know that your U will be between 4 and 5, and for 4 is topological and for 5 is topological, your material will be topological. And we also applied this topological classification that I'm not gonna go through it, but you can find information in this reference here. And okay, so we ran our high throughput search and we found 103 materials with no trivial topology for several values of U, and among them around 50 for all values of U. So it was a quite satisfactory result, given the fact that before there were just a few magnetic topological materials. And these are a few of the nicest band structures. This is an ferromagnetic TI. This one too. These are ferromagnetic semimetals. These are ferromagnetic semimetals that actually display very nice surface properties as well. And again, this has been allowed in a website where everybody can look at the magnetic compound or provide the space group or the ICSD and look at the topological properties as a function of U. Okay, but this is a first step, let's say, because of course we're gonna realize if we have a topological protected semi-metal or not and the dimension of the crossing. But if we want to look for interesting properties, then we need to go further in the study of the bands of these systems. And in this sense, we are interested in also multifold nodal semimetals. And multifold nodal semimetals are nodal points that have more than 1, 2, or 4 degeneracies, and they can host large Chern numbers and very interesting surface properties. So to look for these M-fold energy degeneracy, it was already done some years ago when all these things were not implemented. But basically what we did is look for the degeneracy of the reducible representation of the little group at the high symmetry point. And if we go for large degeneracies, we need to look to non-symmetric groups, because non-symmetric groups combines a unitary symmetry plus translation. And when we combine this unitary symmetry with translation, we enlarge the unit cell in real space. When we enlarge something in real space, we fold it in reciprocal space. So we're gonna have band folded that are protected by symmetry. And of course, we can have high order crossings. And by looking at these large multifold nodal semimetals, we go beyond the Weyl and Dirac paradigm in a sense that this quasi-particle excitation were ever like even considered in higher energy physics. Two of these very interesting lattices or space group are these ones here, where we can find 3-fold degeneracy or 6-fold degeneracy with large Chern numbers. And actually, if we develop the K.P Hamiltonian, we can adiabatically connect it to spin 1 matrices, generalizing therefore the Weyl semi-metal formulation. Okay, this was first down for systems that are non-magnetic and preserve time traversal symmetry and spin orbit coupling, of course. And as I said, they have very interesting surface signature, like double Fermi arcs. not like with the case of the Weyl, where we have Fermi arc. In this case, we have these symmetry protected arcs that actually cross the brilliant zone. Okay, so now we want to apply these to magnetic materials, because magnetic materials are the ones holding these pairs of ideal Weyls, and we were also interested in what happened whenever we have a multifold crossing. So for that, we need to rethink a bit the way we treat symmetries. So we can write the full space group as it's a space group that has all the symmetries for spin up, for example, and then we apply time reversal symmetry and we recover the contribution of the two spins. So we can, let's say, split our group into cosets, the one that has all the symmetries and the one that has the symmetries plus time reversal symmetry. So basically, time reversal symmetry, what happens is that it flips the spin. So whenever we break time reversal symmetry, the spin flipping is not happening. Magnetic configurations are way more complicated versus the 230 space group that we have when we preserve time reversal symmetry. I will have 1651 magnetic groups where time reversal symmetry is broken. So it can happen that it's broken, or it can happen that it's combined with other symmetries like translation or mirror or rotations. But what cannot happen is that it cannot appear by itself. Okay, so with this idea, we're gonna divide the type of magnetism that we can find in materials in four. Well, it's not as this is what group theory people do. First is type 1, where time reversal symmetry does not happen and we have commensurate magnetism. Type 2 has time reversal symmetry preserved. It's the magnetic structure, let's say, that we find over nil temperature with no magnetic moment and the spins. So basically, time reversal symmetry flips the spin. And then whenever time reversal symmetry is combined with another unitary symmetry and they create an anti-unitary operator, we'll have type 3 of type 4 when the translations are not fractional, and we'll have type 3, and when they are fractional, we have type 4. But when this way of formulating the magnetic groups, what we find is a common group to all of them that can relate the different brilliant zones and actually give us the information that we need about the degeneracies that we find at high symmetry points. And what we find is that we cannot go beyond the eightfold degeneracies as in non-magnetic materials. And the K.P Hamiltonian basically are the same, the physics are the same, and we can find these degeneracies in these magnetic groups in these Wyckoff positions. And also there is more information in this paper. And while we predicted the existence of type 1 in a threefold material, which is this one here, manganese 3 iridium silicon, when we add a U of 3ED, we have these threefold crossings at the Fermi level, and it has antiferromagnetic configuration in a cubic space group with polarized bands. So we hope that experimentalists one day will grow this material. Now, now that I have introduced the theory part, I want to present to you some collaborations with experimentalists that are quite interesting, detecting these topological phases. The first one is an European Carmion arsenide, and I would like to convince you that actually this is ideal Weyl candidate. So European Carmion arsenide in a ferromagnetic configuration along the z-axis, because it has belongs to the hexagonal space group P-3M1. In the gamma direction, here and close to the Fermi level, displays two crossings that have a linear dispersion and actually come in pairs, and it's clean of other bands. So how do we get here? So let's start with the ground state. So the ground state has in-plane magnetization. In the absence of a magnetic field, we calculated the band structure and we have an antiferromagnetic insulator. However, whenever we apply a magnetic field below over a critical magnetic field, we can magnetize the sample in the z direction. And what happens is that bands split, they cross, and we have these two Weyl crossings at the Fermi level. But this, of course, these calculations were done with DFT, and we mimic the external magnetic field by inducing a ferromagnetic phase, a ferromagnetic monument in europium, and we need to make sure that our DFT actually is able to reproduce the main properties of this material. So for that, what we do is ARPES experiment on europium cadmium arsenide in its common state, and these are the DFT calculations. This is the ARPES data, and actually we find quite a nice agreement, even for a larger energy window. Here we both see the F states and nice dispersion. And they also perform different energy cuts, where we see the dispersion of the bands that we see with DFT. Okay, so at least at the ground state, DFT and the ARPES data agree. And to actually prove that under a magnetic field, we have Weyl nodes, they perform several transport experiments. So they apply an in-plane resistivity up to 37 Teslas, and they see 3 oscillations. On these large oscillations, period is consistent with a small cross-section of the Weyl points. And from the plot, they extract the mass and they look at the amplitude of the Shushnikov, the Haas oscillations, and that indicates that actually the mass, it's small, as it happens in direct dispersions. So the fact that europium cadmium arsenide is a real candidate to ideal Weyl semimetal under a magnetic field, I think is quite convincing. And then I want to talk about a recent experiment we have. Well, our collaborators have from some in cobalt disulfide, a pyrite in a cubic space group. So pyrites are very interesting because they display weight. The family displays properties all along the electronic, let's say, field or band structure field. They are superconductive. They are good for spintronics. I don't know. I mean, they are good catalysts, and well, it happens that they also have very interesting topological properties. So this is the band structure of cobalt disulfide. We start looking at it when we were looking for multifold fermions, but if one look at the band structure, it is clearly unstable. So either it has to become a mod or it has to magnetize. And in this particular case, what happens with cobalt disulfide, it magnetizes. And it magnetizes, it has what is called soft magnetism. So it doesn't have a particular direction, and actually it's very easy to modify under a magnetic field. So we decided to pick up the Z direction, and anyhow it's a cubic structure, so it doesn't change much if we choose another one. So we'll have this crystal structure with this magnetization, and now we want to do the DFT calculations. And when the classic question arises, do we need U, do we need LDA, what GGA, what pseudo potential do we need? So we did different calculations, and we saw that with LSDA, I mean local density approximation, we could find here a minority pocket, whereas with GGA we couldn't. In principle, the choice would be like GGA with U equals 3, for example, which is a value for cobalt that has been used widely in the literature. But surprisingly, no, this was not the case, because this minority pocket that we see here at the R point can only be reproduced by LDA. So this pocket here. So actually we have facing a material that has itinerant magnetism, and we can agree with the experiment using U equals 0 and local density approximation. So this is what we're going to use for our calculations. And by looking at the bulk band structure and the ARPES, we also could reproduce other features like this fourfold crossing. And it is a very interesting compound, because as we see here, the bands are polarized, which means that if we have anything at the surface, probably it will be polarized as well. Okay, we check different cleavage planes, for example, for U equals 0 and LDA, and we still keep finding very nice agreement that this electron pocket at the Fermi level. We also look at other surfaces and to other energies, and we still find very nice agreement on some surfaces where all the symmetries are broken. We even find this chirality, some sort of chirality of the bulk state. Okay, but it happens that we are like very happy about our agreements, but we want to find topological features. And what actually this material has is it has 4 inequivalent endpoints, and depending on which line we look at, we can find a line node or a Weyl node, right? So we wanted to identify both of them. And as I said, identifying nodal lines is not easy because in this particular case, even less, because we're gonna have our surface state embedded in the bulk. But Inyo and Niels, they figure out that if they could look at different planes where this crossing should happen, they could actually identify if there is a line node. And this is what they did. They look at the one cut in the 1,1 plane and another cut in the 1,0,0 plane, and then they put both of them together, and voila, they saw the line node that we were looking for. And in order to look for the Weyl node, well, in this case, it was in this particular direction. So of course, there is a shifting of the Fermi level, which happens quite often in ARPES, but clearly these 2 lines would cross eventually. And a further, let's say, proof that actually we have Weyl nodes in this material is what we look at the Fermi arcs that actually basically are here, and in the calculations are so in this band structure. So the interesting thing of this material is that it has a completely polarized band structure. So this means that it will also have polarized Fermi arcs, and these polarized Fermi arcs that happen in the surface can be very interesting for spintronic applications, because of course they are protected by symmetry, they are topological, and they are very robust under surface passivation. And with this, I'm gonna finish with this talk. So I introduced magnetic topological quantum chemistry, a very fine tool to look for topological semimetals. We found with this of the order of 100 magnetic materials, and beyond time reversal symmetry, I show you that we can also predict magnetic crossings, and I presented to you 2 experimental realization of 2 very interesting materials that display topological properties. And I thank you all for your attention.
So thank you very much, Maia, for your exciting talk. So we have time now for questions. And if you would like to ask a question, write it in the chat or raise your hand. So then you can ask your question orally. So so at the moment, we are still waiting for questions. So Maia, for the time being, maybe I ask one. So in the beginning of your talk, you presented the symmetry analysis. And so I was just wondering in how far these topological constraints are inherited by experimental observables. So I'm in particular referring to optical spectroscopy. So my question is actually, how can I use optical spectroscopy to decide whether some material is topological or whether it's rather trivial in terms of topology? Is there some rule, or do we really have to use ARPES and then go into the band structure and well, look into the details of the bands?
No, you can use also, I mean, as I said here, there are other ways of identifying topological properties. In this case, there are no bands here. It is not possible to actually do ARPES experiment on material that needs an external magnetic field. So for example, these transport properties can also give you a hint that actually there is a Weyl semimetal. And with optical conductivity, for example, they look for quantized response. I can give you some reference if you're interested. Mm-hmm. And optical spectroscopy, I'm not sure.
Okay, I was just wondering whether there's some general principle that also carries over to symmetry, or whether you really have to go into the microscopic details and then decide whether what you observe is more trivial or topologically related.
I mean, please, like it's a electronic properties mainly related with transport. So usually it's transport experiment that gives you the hint whether you have a topological material or not.
Okay, thank you very much. So there is a question now from George Zipperline. You can please unmute and ask.
Oh, hello. Is my microphone working?
Yes.
I'm sorry if this is a little far afield, but I'm curious as to whether you have looked at quasi-crystals with like a Penrose tiling kind of symmetry and the topology that might happen there.
Well, there are some works where they have looked at quasi-crystals. I haven't looked myself. As far as there is a way of preserving translation, and in quasi-crystals there is, if you add one extra dimension, you can apply this method. There's been like some works on amorphous topological insulators, and they still found the surface state, and in quasi-crystals, I think they found some surface states too, but I can't tell you 100% sure. I'm just saying that we can apply the method in quasi-crystal with some work.
Thank you, that's fascinating. And I very much appreciate that you tied this into the group theory and theoretical aspects. Thank you.
Thank you.
Maia, so there's a question in the question and answer section. If you click on it, you can read the question and answer. If not, I can also read it. Can you see it?
Yes, I'm reading it. May I say the little at most three-dimensional? And even if they are spin degenerate, they are up to six-dimensional. If you consider. Yes. Yes, because you have a, yeah, of course, you have a translation operator.
Maia, can you please read the question and then?
Okay. I thought, okay, so no, I thought everybody could read it. My understanding is that little representation are at the most three-dimensional, and even if they are spin degenerate, they are up to six-dimensional. If you consider the co-representation, you see that it is eightfold degenerate is because the translation operator, yes, you need a translation operator. I mean, an anti-ferromagnetic phase, for example, you will have the translation operator.
Okay, thank you. Are there more questions? So if so, please raise your hand. At the moment, I cannot see it, and in the chat not either. So I would.
Hassan has a question. Sahid.
Oh yeah, Hassan, please go ahead.
How many magnetic material could be topological? You mean in the world?
I had a comment in connection to earlier question. So yes. The optical quantization, say CPG quantization in Weyl semimetal, it's not that robust. It's kind of one of those weak, in response to your question, Tobias's question about optical. And that it's very fragile quantization. With little bit of interaction, it goes away. So that was the response to your earlier question.
Thank you.
But Tobias was asking about optical spectroscopy, which I'm not sure is the same as optical conductivity.
No, nonlinear, or CPG is nonlinear optics. I do CPG. I did that measurements myself.
All right.
Okay, so I cannot see any more questions. Just let me check. No, I think we went through all of them. Good. Yeah, then thanks a lot, Maia, again for your exciting talk. It was a great pleasure. And I guess later we have talk. We still have time after the last talk to meet in the separate sessions, yeah, and the breaks to discuss further. Okay, so then we have 2 minutes left until the next talk. And yeah, for a very short break. Thanks again, Maia, and yeah, see you later in the discussions.